All right, welcome to another version of me talking a lot. I'm your host, William Viebert. Let's talk about inference and sampling variability. Like we've been saying, no two samples are going to be identical, right? Samples are different every single time. That's what sampling variability is. If I took one sample out of Boone High School and then took another one, the chances that they're the same are so low. But if we use a larger sample, that's a way that we can reduce sampling variability, because if I'm talking to more people, I should get better guesses, right? Like I'm getting more information. A result, when you do an experiment, you can eventually find a probability. And that's going to be this important but confusing thing in a second. But a result is statistically significant if it's too unusual to have occurred purely by chance. Now, this is very particular, and I know you probably didn't do the experiment because it's kind of hard to do without a facilitator for it, which makes sense to not do it because of that. But the way we determine if something is unusual, we assume that something is true. So say I want to know if the mean height is greater than 68 inches. Right, so I want to know if the mean is bigger than 68 inches. Then what I do is I assume that the mean is equal to 68 inches. Right, so I make this assumption. I say, well, what if it is 68 inches? Then, and in my sample, right, remember X bar is the sample, mu is the population. In my sample, I saw an average of 70 inches. So then what I end up trying to find is the probability that I'd have a sample greater than or equal to what I did if the true mean is 68, right? That's how we determine statistical significance, and it's a weird idea. You make an assumption about the population, and based on that assumption, what are the chances you saw what you saw? We calculate that probability. It's called a p-value. You'll get to it later. But that's what we do. Once you find that probability, anything below 5% is considered statistically significant. Now, when you do this in the notes and assignments in this unit, that means you're probably going to be counting a lot of dots, because what they're going to do is they're going to simulate it. They're going to say, okay, well, suppose that the mean is 68 inches. Here's a bunch of samples of what that would look like. How many of them were weird? So count up the dots that were correspond. So for me, I would have counted the dots that were 70 or higher out of, maybe they ran the simulation 1,000 times. And that's how you'll get your probability. That's how you'll figure out if something's unusual. All right, some students at your school claim that listening to music while studying will help improve their GPA. 4 studies are proposed to determine the effect. At the end of the study, it was found that those who listen to music had lower GPAs. Our goal is to make conclusions based on 2 things. 1, how the study was designed. 2, the fact that lower GPAs were in fact found in people that were listening to music while studying. So there's 4 different experiment setups that we're going to look at. Here's our first one. Get all the students in your stats class to participate in a study. Ask them whether or not they study with music on and divide them into 2 groups. Is this random sampling? No, you got the people close to you. This is convenience sampling. Is there random assignment? No, you ask them, do they listen to music? So then what's the extent of our conclusions? Well, we didn't do an experiment, so we can't get cause and effect. We didn't do random sampling, so we can't say that's true about a larger group. So we can say association in this group only. That's all we got. Nothing better. That's not very good, right? So hopefully that shows you that you random sampling and random assignment, at least one of them needs to be there. All right, study number 2, select a random sample of students. Oh, well, I got the answer to number 1. Yeah, that's random sampling. To participate in a study, ask them whether or not they study with music on and divide them into 2 groups based on their answer to this question. Is there a random assignment? Nope. You ask them what they already do. So then what's the extent of our conclusion? Random assignment is what gives us causation. I don't have that. So we have an association we did a random sample students from your school. So in the population, so there's an association between listening to music. I'm writing a little more thoroughly this time. And lower GPA in the school, right? So you can generalize to the population from which you sampled. That's as far as you can get. Get all the students in your stats class to participate in a study. So that's not random sampling. Randomly assign half of them to listen to music while studying for the semester and half to abstain from listening to music while studying. Then yes, we do have random assignment. So I can't generalize, but I can say cause. So in this class, listening to music while studying caused lower GPAs. I can get causation, but I can't do generalization. Now, if you just had to guess, study number 4, what might happen? Oh, look, random sampling and random assignment. This is the ideal, right? We get generalization and we get cause and effect. So listening to music while studying causes lower, and I'll even say likely, right? Because I don't know 100% for sure, but likely causes lower GPAs. Ew, what am I writing? For students in this school. And as far as we can get. All right, key takeaways is what's there, right? So random sampling gets you generalization of the population. Random assignment gets you cause and effect. And that's what this table summarizes. Last little bit, for decades, researchers have tried to establish explicitly that smoking cigarettes causes cancer. What issues arise with this? How do we get causation? Causation comes from experiments. So I guess to get cause and effect, what we would have had to have done is pick 100 people, make 50 of them smoke, make 50 of them not smoke, and then see who gets cancer. That doesn't seem to be a great thing to do to people if you think it might happen, right? If you think that smoking causes cancer, it'd be a pretty jerk move if you started making people smoke. And honestly, it's true back here too, right? If you think listening to music while studying lowers GPA, it'd be a pretty jerk move to make them do it. So whenever we do these experiments, there's these ethical dilemmas, and we have to really, really be careful about them. We have to think like, okay, well, what are the implications of that? And we need to tell the person, right? With a person that, I don't care about that. The person that is involved in your study, they have to know the risks. So that's called informed consent. You have to get informed consent from experimental units. Both of those words are important. Informed, they have to know everything they're getting into. Consent, they have to agree to it, right? So both words are necessary. You can't just say, hey, you want to do my experiment? And they say yes, because they didn't know what was going on. I mean, you can't just tell them, hey, this might happen, and then do it to them anyway either, right? Both of those words are critical. Results have to be confidential. That's just respect people's privacy. Institutional review boards exist, and they will oversee researchers to make sure that they're performing their experiments ethically. And goodbye.